Hello folks, so in these couple of videos I want to present to you this fascinating story of SunPower and their cell. And this cell is one of the most efficient crystalline silicon based solar cells that you can buy. And you can, it's not just a laboratory cells. You can buy these panels from Home Depot and install them on your house. And these solar cells achieve efficiencies, the latest generation of them achieves the efficiency of solar conversion of more than 24%. And the cell design, what SunPower calls them as the Maxion, third generation of these Maxion cells. And on a module level, they achieve efficiencies of more than 21%. And these modules, they have very nice characteristics. They have a low temperature coefficient of efficiency. They have a better immunity to humidity, and better thermal cycling and so on. All of those nice characteristics that come along on the module level results from this very unique cell design that SunPower has, and they are leveraged into all these nice characteristics that the module gives. So a SunPower cell, it looks very different from a conventional crystalline silicon cell that you must have seen. So if you look at the front side of it, it looks very elegant. It looks all black. So there are no fingers or grid lines. These metallic grid lines which are usually present in a conventional crystalline silicon cell. So none of these are present on the SunPower cell, and it looks completely black. The contacts and the real magic of this device is located at the back. So both the P and N contacts, they are located at the back, and they're located in this interdigitated fashion, such that, let's say, these lines I'm drawing, they represent the N-type contacts, so they're all collected like this. And then the P-type contacts are interdigitated. That is, these P-type contacts are essentially interdigitated between these N-type fingers. And this cell design, it's also called as interdigitated back contact cell, or IBC cell design. The way, as a result of the way these contacts are formed in this interdigitated fashion. So let's take a deeper dive and look, what's actually goes inside this SunPower cell and some of the unique features. So I'm plotting over here. I'm drawing over here this cross section of the cell, and I've inverted the cell. So essentially, the light is incident on from this side, and all the metal contacts are located now on as shown over here on the top. So these contacts now, since they're all located on the side which is not facing the sun, I can now essentially make these contacts as tall as possible without worrying about that they will interfere with my light when it's incident at oblique angles, or I can even make them very wide without worrying about the shading losses. As a result of that, I can minimize the resistive losses which are usually associated with these fingers and these bus bars, because now I can make these contacts, I can make them wide, and I can also make them tall. And also, since these PNN bus bars over here, these are interdigitated, so these since we have this interdigitated design, these electrons and holes which are generated inside the silicon, they can be now collected close to each other, so none of them have to travel very far, as would have been the case if I don't use this interdigitated design. So it kind of helps in minimizing the resistive losses which are associated with these contact schemes as well. Sometimes, and actually now the latest generation of says that SunPower says these things are actually made pretty thick, and they're made using copper electroplating, and they offer the additional advantage that they provide a mechanical strength to the cell. So even though your cell can crack, so these these copper plating of these interdigitated contacts at the back, it the cell can still deliver decent efficiencies and good power conversion if you have these metal grids at the back, which provides mechanical strength to the cell as well, as compared to a conventional cell where the cell is held together just by the mechanical strength of this silicon. So some of the other unique, nice features of the cell are illustrated in this figure. So this cell, it uses this anti-reflection coating and texturing on the tops to minimize light reflection and maximize light trapping, just like a conventional solar cell does. Some of the unique things that it has, that the cell uses N-type silicon as compared to most of the conventional cell which use P-type silicon or P-type wafers for making these cells. So one might wonder why this is the case, because in N-type silicon the minority carriers are holes, and versus in a p-type silicon, the minority carriers are electrons. So usually you tend to maximize the collection of your minority carriers, and since holes have lower mobility as compared to what you get for electrons, this at a first glance it might seem a counterintuitive way of making these cell design. But there are a lot of other technological considerations. One is that these N-type silicon wafers, they are less susceptible to a phenomena called light-induced degradation. So whenever you shine a lot of light on these cells, the efficiency of these cells degrades, and that especially happens in cells made out of p-type wafer, because these p-type wafers have these boron, and then they combine with these oxygen present in the wafer as well to form these boron oxygen cluster, which can cause up to 2 to 3% decrease in the efficiency of the cell in the first few weeks that this cell is being used. While those things, light induced degradation effects, they don't occur in the N-type silicon. Also, this N-type wafers, they are very immune to impurities such as iron and so on, which are present in the feedstock of what is used to make these wafers. So because of both of these things, its immunity to impurities and no presence of these light-induced degradation, in fact, the N-type silicon can give a higher diffusion lengths as compared to, even for the minority carriers, as compared to P-type silicon. And that's why this N-type silicon is used in the SunPower cell. And in fact, if you look at some other companies which are making these high efficiency silicon cells, such as Sanyo, which makes the HIT cell, or more recently Yingli, it makes a series called the Parna cell. They also use the N-type silicon because you can get higher efficiencies as a result of these better diffusion lengths that you get in N-type silicon. So that is a unique feature number one. Another thing that you notice in this design is that both your P plus and N plus diffusions are located at the back. So this P plus diffusion helps in forming a selective contact for holes. This N plus diffusion similarly helps in forming a selective contacts for electrons, and they are located at the back. Also, they are localized, so they all of the carriers which are generated inside these diffusion regions, they are not collected with a very high efficiency. So now these things are localized and located at the back. So they minimize the generation in this P plus and N plus region. At the same time, they helps in forming these selective contacts for electrons and holes. So that's another unique feature, probably unique feature number two. I already talked about these backside contacts, with another unique feature. Then also there's this mirror located at the back. So this mirror especially, it reflects back these red photons, or these these high wavelength photons, which might not be absorbed during the first or the second reflection, and it reflects it back into this silicon with a very high reflectivity. So that's another feature of this cell. The other feature that I want to point out is that the use of this lightly doped diffusion in the front. So let me illustrate the need for this lightly doped diffusion using a 2D cross section over here. So let me compare the 2D cross section of a conventional cell. So in a conventional cell, you have a p-type wafer, and then you have an n plus emitter at the top. So you have this n plus emitter, and you have this emitter contact at the top, and at the back you form this p plus back surface field using this aluminum line. So there's the electric field which is present inside this conventional solar cell, which helps in separating this carrier. So it helps in electrons being collected on the emitter side, and it drives these holes which are generated inside this depletion region over here to the back surface. But at the same time, we have this contact which is present at the top. So this one causes shading. Also, a lot of the carriers which are generated inside these emitter regions, so the electrons and holes which are generated inside this emitter region, they get recombined very easily because this region is heavily doped. So especially the lifetime for these minority carriers, these holes which are generated in this emitter region, is very small. So versus in comparison to that, what has been done in this IBC design that SunPower is using is that you have moved both your P and N contacts towards the back. So you form these localized P plus and N plus diffusion, and then you form these interdigitated contacts at the back. So it helps in minimizing this shading loss because there's nothing facing the incoming light from the top. But at the same time, there's this electric field which was helping me separate the carriers is no longer present in this design. So as a result of that, you need a very good high quality, you need a very high quality of the semiconductor material such that the diffusion length for these carriers which are generated, these electrons and holes which are generated, are long enough such that they can be collected at these P plus and N plus contacts without getting recombined. So that's one of the reasons you used this N-type substrate, because it gives better quality, better immunity to these impurities in your silicon. So this is fine. So now why do I need a surface field at the top? The reason is that even though I passivate these top surface using silicon nitride or a combination of silicon oxide and silicon nitride, the surface recombination velocities at the surface is at best, something around 100 to 200 to 300 kind of a range. So even though I passivate the surface recombination is still a dominant cause of dominant loss mechanism, especially in this case since there's light coming, and especially this blue light, it will generate a lot of these electrons and hole pairs very close to the surface, and they can now essentially go to the surface and get recombined without getting recollected at this back. So what is done over here is that you form a very lightly doped junction at the top. So this wafer was N-type to start with. So you dope it with a very light P diffusion at the top, and it creates this surface field at the top, which repels these holes from getting entering into this region, and essentially pushes them back, just like back surface field over here does. So this helps in minimizing the surface recombination. At the same time, you keep it you don't dope it very heavily, so that the carriers which are generated in this region can still be collected without getting recombined. So that's the reason why you still keep a lightly doped diffusion at the top to minimize these loss which are happening at the surface. So in this video, I've talk to you about some unique features about this SunPower cell. In the next video, I'll discuss the process technology and how SunPower was able to drive the cost of this IBC design down and produce it on a mass scale. So see you in the next video.